There we are. And for all of you that may be listening in the audience, or those of you that are speakers that belong to groups in astronomy, you might want to share this program. This is an educational outreach program by the Astronomical League. And the way we do outreach is by sharing.
We all know what a galaxy looks like, right? It's a huge collection of stars and other matter that's shaped like a spiral or an ellipse. And if you're an astronomy fan, you probably know that most of the mass is from invisible, mysterious material called dark matter. Well, NASA's Hubble Space Telescope just took an image of a galaxy that is none of those things. For the first time, astronomers have strong evidence for a galaxy not having a significant amount of dark matter. Most astronomers currently believe that dark matter plays a fundamental role in our universe and the formation of galaxies. This is because galaxies seem to have a lot more mass than what we can account for based on just the stars we see. How much mass is in a system is determined by measuring the speed at which galaxies rotate or individual stars in a galaxy move. Without the gravity from that mass, a galaxy would fly apart if everything in it is moving as quickly as we observe it moving. Decades of research have led astronomers to the extraordinary conclusion that 85% of the mass in our universe is invisible in all wavelengths of radiation, and that it's composed of matter that does not contain protons or neutrons or any type of particle we've detected before, and that this invisible material is all around us, passing through us without interacting with regular matter except by gravity. For some, that's a tough pill to swallow, and a minority of astronomers wonder if maybe we just don't completely understand how gravity works. If that were the case, and it was an inherent property of gravity that causes galaxies to move the way they do, then we could expect all galaxies to behave the same way. In other words, they would all seem to have about the same portion of dark matter. But with the galaxy in this Hubble image, astronomers looked at the velocities of 10 globular clusters in the galaxy, each a spherical collection of hundreds of thousands of stars, and calculated that their movements can be accounted for entirely by the mass of the visible material in this system. That means this galaxy has little to no dark matter. Strangely, this absence of dark matter actually provides evidence that dark matter is real. It shows that dark matter isn't always coupled with regular matter, that it's something separate. You can have regular matter without dark matter. This galaxy is really weird even beyond the dark matter thing. You may have noticed you can see straight through it. That's because this galaxy is what's called an ultra-diffuse galaxy, which, as the name implies, is extremely low density. This galaxy is about the same volume as our own Milky Way galaxy, but only has about 0.5% the amount of stars. Though astronomers have known about ultra-diffuse galaxies since the early 1980s, they can be difficult to find since they're so faint. A team of astronomers is using an array of telephoto lenses called Dragonfly to seek out these ghostly-looking objects. They obtained observations from Dragonfly, the Sloan Digital Sky Survey, the Gemini Observatory, and the Keck Observatory, then requested time on the Hubble Space Telescope to take a closer look at this unusual galaxy. Having images and data from multiple sources allowed the team to determine that this galaxy does not have a significant amount of dark matter. This was definitely surprising to find. No other galaxies so far have appeared to be so lacking in dark matter. In fact, other ultra-diffuse galaxies seem to have an overabundance of dark matter. The same team who studied this galaxy discovered a different ultra-diffuse galaxy in 2016 that they calculated was 99.9% dark matter. Yet another weird thing about this galaxy, the globular clusters used to measure the galaxy's rotation are way brighter than normal globular clusters. The researchers have written a different paper that focuses on just these oddball collections of stars. So this is a very strange galaxy in several ways. Astronomers will be looking at Hubble observations of other ultra-diffuse galaxies to see if there are any other examples of galaxies with unusually low or high amounts of dark matter. With more samples, astronomers will be able to better understand the nature of dark matter, the formation and evolution of galaxies, and the overall structure of our universe.
Well, hello everyone. This is Scott Roberts here, and we're introducing the Astronomical League Live number 3. And this is with keynote speaker Rachel Cionitti. And it's my pleasure to introduce the other people here. Just to get started, we have President Carol Orge with us. We have Don Knabb, who will be speaking. Terry Mann, who is a former 2-term president of the Astronomical League and secretary of the league now. Dr. David Levy, who will be opening our program today. Of course, Rachel as well, and giving the keynote. Chuck Allen, former president of the Astronomical League. And John Goss, who I think also is a former president. In fact, I know he is the former president of the Astronomical League. So we're all here during this chilly winter night here. It might be warm where you are, but it's cold here. So I'm glad to be here with warm friends and here with another exciting program with the Astronomical League. Terry, I am going to turn this program over to you, and this is going to be exciting.
Thank you very much, Scott. It is so nice to be able to see everybody again. It's so great doing Zoom because at least if I can't see you in person, I'm seeing a lot of you, probably more than I would if we were doing this in person. So it's really been nice. Thank you all for being here, and thank you for everybody that is watching. We really appreciate it. So it's my pleasure to introduce David Levy. Now, David and I go back a few years too, and his wife, Wendy. I have been at their house, and they are just amazingly friendly people. I had such a great time there. And David and I have ran into each other too at some different conferences. We sat on the same board at one time. So our history kind of goes way back too. And I've always enjoyed everything that he has said and loved his books. So David, thank you for being here, and I am going to turn it over to you.
Thank you. Thanks, Terry, and thanks, Scotty.
Mhm.
And I'm really very happy to be here tonight to help introduce our speaker, Rachel, tonight, who's going to give an excellent lecture. I am supposed to give a quote from Shakespeare at the beginning of every one of these events. So I looked through every word of William Shakespeare till I found something about Rachel, and here it is. Rachel will be lecturing hereafter tonight. There will be a time for such a word. Tonight and tonight and tonight creeps in its roaring pace from night to night to all the syllables of recorded time, and will continue to be heard after that. Light, light, brief candle. Life's but a racing football player, a rich player that shines his hour upon the stage and then is heard forevermore. It is a tale told by a genius, full of sound and fury, signifying everything. Now, of course, this is obviously not by Shakespeare. It's a little bit by Shakespeare, and a few little things changed to make Rachel feel a little better. But I actually did find something by Shakespeare that actually does deal a little bit with dark matter and energy, but not in the sense that we would see it in the 21st century. It is an attempt by Shakespeare to actually talk about an eclipse of the sun where darkness appears. He does not mention the word eclipse. He does not mention the word darkness. And Wendy and I found out about this particular quote when we were on a cruise, and somebody actually mentioned it. It's turns out to be one of my favorite quotations. And this is also from Macbeth. He talks about an eclipse of the sun this way. By the clock, 'tis day, and yet dark night strangles the traveling lamp. Is it the night's predominance or the day's shame that darkness has the face of earth and tomb when living light should kiss it? Thank you, and back to you, Terry.
Thank you, David. That was very nice. Appreciate that. I would like to go ahead and move on to Chuck Allen. And as he was just introduced, Chuck is a past president of the Astronomical League, and he is the current vice president of the Astronomical League. And he is here to speak about the awards. So Chuck, I'm going to turn that over to you.
Thanks, Terry, and good evening, everyone. I'd like to go straight to a slide set, if I may. If I can share a screen here. And we'll go here. On the current slide. And what you see here is why I'm speaking with you tonight. It is League Awards season. And this is very important whether you're a member of the Astronomical League or not. So you might want to pay attention here. And if you are in an Astronomical League club, this may apply to some of your members as well. Let me start with our youth awards. The youth awards that we have start with the National Young Astronomer Award, which spotlights research done by young people of high school age. For this award, you need to be a United States citizen or enrolled in a U.S. high school between 14 and 19 years of age at the time of nomination, and not enrolled in college. If you're taking an isolated course in college, that's okay. Just let us know and we'll make a determination on that. This award is sponsored. Here's our current winner from 2020, Karen Levy, who did an incredible amount of research, actually determining for the first time the source of neutral 21 centimeter hydrogen source in the sky, something that even professionals had not done hitherto. This award is sponsored by our host tonight, of course, Scott Roberts of Explore Scientific. He provides wonderful telescope prizes to our winner. Our winner is brought to the national convention each year and receives a great plaque. So we would encourage you to add this to your resume before you apply to college. We also have youth service awards that are sponsored by the Horkheimer Charitable Fund. We have the Horkheimer Smith and Daria Awards. They're really 2 awards that are given if you apply for the service awards. And these awards provide large cash prizes. And the winner of the Smith Award is also given a trip to our national convention to receive the awards. In addition, we have the Horkheimer Parker Youth Imaging Award, which goes to young people who engage in imaging. Again, this is for under 19s. You see, we have large cash prizes for this as well. And we have a journalism award for league members who are 8 to 14 years of age. It requires the writing of an essay not to exceed 500 words on a scientific topic. Does not necessarily have to be an astronomy topic. So we would encourage club officers, any club member, if you have young people in your club who have engaged in service or engaged in imaging or are interested in writing, please have them enter these award programs. The deadlines are all March 31st. We also have national awards. The start of that, of course, is our highest award, which is the Astronomical League Award, here being received by Richard Gott of Princeton in 1998. We have, in addition to that, the Mabel Stearns Newsletter Editor Award. Submissions for that are due by March 31st. We have a Webmaster Award. So if your club newsletter editor or your webmaster does exceptional work, please consider nominating them for this award. We also have a Leslie Peltier Award, which goes to people who engage in extraordinary observing efforts and achievements, and nominations can be made for this as well to the committee. Jim Fox here is a winner, for example, of our 2014 Peltier Award for doing photometric research on the atmospheres of Uranus and Neptune. We also have a sketching award, which provides cash prizes to its winner, sponsored by Astronomics. And soon we will be announcing an Explore Scientific sponsored imaging award. We haven't worked out the details of this yet, and the deadline will probably be later than March 31st. And so watch the website for that. And we'll be making announcements in future live events about this. We also have a new award for imaging that is open to female league members aged 19 and over. Right now, we're working on sponsorship of this award. The deadline will be later. It'll be May 31st because we need to announce this in Reflector in March. We also have the Horkheimer Library Telescope Program. The league gives out to one club in each of our 10 regions a library telescope for them to place in a library near them. Clubs must enter this before the March 31st deadline, and this too is sponsored by the Horkheimer Charitable Fund. And this is a very popular program linking you with libraries in your area. Applying is easy. I will caution you that our website is undergoing a major transformation right now. We're moving from one platform to another. So some of our pages are a little out of date, but they still work. So go to our website at www.astroleague.org and look for awards on the menu on the left side. And when you get there, you'll find a number of links in yellow along the left side of the column here. And choose the one you're interested in. National Young Astronomer Award. Jack Horkheimer Service Award should actually read Youth Awards because this link goes to all of the Horkheimer Awards. Mabel Stearns here and so forth. Once you click on, let's say, the Horkheimer Awards, you will find mention of our Service Awards, our Imaging Awards, and our Journalism Awards, and direct links to pages that will take you to application forms. These forms may read 2020, don't worry about it, just submit it. Some of them have instruction sheets to make it clear what we need from you in applying for these awards. So here's the summary of what we have. We have the 4 major youth awards. Actually, it's 5 because the service award is double. As you see, you do not need to be a league member to apply for the National Young Astronomer Award. You do need to be a league member within certain age parameters for the other Horkheimer Awards. Our Astronomical League Award is open to anyone. The Webmaster and Mabel Stearns Sketching, Fleming, and Explore Scientific Imaging Awards will be open to league members, and the Fleming Award has some additional requirements. Again, please nominate someone or apply yourself for these awards. All of the deadlines are March 31st of this year, except for Wilhelmina Fleming, which is May 31st, and the Imaging Award, which will be announced shortly. If you have any questions or can't find a form that works or have any trouble at all, contact me. My email address appears at the bottom, simply vicepresident@astroleague.org. And I'll take care of any questions you have or allow you simply to submit to me, and I'll make sure it's considered. So that's the awards program that we're working on right now. And I hope you will take some time to consider whether some of your members or perhaps yourself is deserving of recognition by the Astronomical League this year. Thank you very much, Terry.
Thank you, Chuck. I appreciate that. Yes, just please bear with us as we are working on the website, changing platforms. Chuck is very quick on email. If there's any problems, definitely drop him an email. And now what I would like to do, as you know, we give away door prizes. And on this event, we will be giving away that doesn't work very well, does it? 3 calendars. Let me find the right spot here.
Disappearing.
3 Astronomical League calendars, and they are really fantastic. I have really enjoyed it. There is something almost on every day in this there really is in this calendar, and the images. They're really nice, very nice, and the proceeds will go to the youth program, to Alcon Jr. So we really appreciate your support there. And so we will be giving away 3 of these, 1, 2, 3 of winners. And what you are going to do is send your answers to secretary@astroleague.org, and you're going to see this on the bottom I'm going to share my screen, on the bottom of each slide here. And so I'm going to ask these questions as soon as this goes. But what I would like to start with is, as we do on every slide program that we do for these questions, we want to warn you about looking at the sun without the proper filters. You do not want to do that. Anytime you look at the sun, make sure you have the proper filters on your telescope or your binoculars. I've had people come up and ask me if just looking at through sunglasses wasn't fine, or if I put on 2 pairs, isn't that good? And no, we definitely don't want anything to happen to anybody's vision. Always make sure when you look at the sun, you use a certified solar filter. And anytime you have any questions about that, contact somebody before you ever look at the sun without filters. Never do that. And this is a calendar. As I was trying to show you, this is much better. It gives you an idea of what it looks like. And every day in there has a bit of either league history or what's going on in the sky, information about the other picture that is also with that calendar page. They're fantastic calendars. Now, first question. Let's say you're going to participate in a Messier marathon, and it's going to be in March, and it's going to be in the mid-northern latitude. What object will be your challenge object? It will be the last object you view in the morning. And send your answers, as I said, over here to the side to secretary@astroleague.org. And I will be giving the answers after Rachel's talk. And so the winners will be announced before the end of this program. And so put your answers in as soon as you can. Second question, the flooded floor of Cassini craters shows many impacts. Which is the largest crater that sits entirely within the rim? And the last question, this looks like Big Bird to me in the middle. Hubble took this image. What object is this? And send your answers in as soon as you can. secretary@astroleague.org.
Terry.
Yes.
May I interrupt just a moment
Go
to add
right
something?
ahead.
Something came to my attention about the solar warnings that we give. And since we may have young people watching this tonight, I'd like to add something just as caution. You may go to events that are sponsored by local astronomy societies where telescopes with very sophisticated white light and H-alpha filters are being used, and you can safely observe the sun through these instruments. Do not think, though, that that means you can look through any telescope at the sun. Those are special telescopes, and most telescopes don't have that equipment on them. So make sure when you're talking about solar observing that you're with someone who knows what they're doing and they're using professional equipment. And let me add also, if you're not in a league club and you're interested in some of these youth awards, you can join the league for $20 if you're under 19. We have membership at large for that. Thank you, Terry, and I'm sorry to interrupt you on that.
No problem, Chuck, but that brings up another another thing too, sky puppies. Maybe we should talk a little bit about sky puppies. Could you talk a little bit about that?
Yes. We have a number of observing programs. In fact, the Astronomical League has the most robust series of observing programs of any organization in the world. We have more than 80 of them. These programs require people to observe a certain list of objects, sometimes to sketch them, and always to describe them and to log information about the observation site, transparency, seeing, and other conditions. For example, one program would have you observe 110 planetary nebulae or 100 globular clusters or the entire Messier catalog as examples of 3 of them. But we also have beginner programs, programs that are highly suited for people just getting started in astronomy. These programs teach you fundamentals about star hopping to targets using charts, understanding right ascension and declination in the sky, recognizing key asterisms that are visible to the unaided eye or to binoculars. And these are important. Sky Puppies is one of these. Beyond Polaris is one of these programs. The basic Messier program is not difficult, for example. And we have an urban sky program. If you have to observe from your backyard in a light polluted area, you can do that program or one of our lunar programs. And these are really exciting programs to pursue, and you get a great sense of achievement from doing them. So I would encourage you to go to our website and go to the observing programs page and find yourself a program that is suitable for that. I do have a slide that summarizes some of the basic programs, but I don't have quick access to it, Terry, but I'll be happy to bring that up later if you'd like.
Sure. And Sky Puppies, if I'm not mistaken, correct me if I'm wrong, can be a free program for kids under 10.
That's correct.
They do not have to be league members. It could be anybody, a child under 10.
That's correct.
So that's something to consider, especially if you're a teacher out there and need any information about Sky Puppies. Please get on our website, astroleague.org, and check that out. And I think it's Aaron that is over that.
Yes.
I think, yeah. Okay. And so Aaron will get back to you, but I think that's a great benefit to have for any child that's just getting started in astronomy. And it will help the parents learn too if they don't know much about astronomy. So I think that's an amazing deal there. So thank you, Chuck. I really appreciate that. And right now, John Goss, you're going to be up. John, as we said, is a past president of the league, always involved in a lot of things. He's media director right now, and he is, wearing all kinds of hats. And he is also chairing our 75th anniversary, which will be in November. So, John, give us your talk, and let's see what's going on.
All right. Thank you, Terry. Actually, this is a real pleasure to be speaking with everybody tonight, because we are celebrating our 75th year as an organization. It all began in November 15th, 1946. So we aren't quite 75 years yet. But back then, we only had about $67 in the bank account and about 1,500 members. Today, I can't tell you how much we have in the bank account, but a lot more than $67. And we have a lot more than 1,500 members. Right now, we're up to about 18,000. I don't think we've broken 19,000 yet. But over the past few years, our membership has been going up, 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 and up. So it's been really, really good for the league and really good for amateur astronomy. The more members we have, the more we can do for amateur astronomy as a whole, and our membership in particular. Since the 1940s, you can imagine all the changes that have come about in the science as well as in the hobby. There have been a lot of changes, but in our hearts, though, I think we're the same type of people as we were back then. You know, back then we liked observing, we liked being out under the stars, we liked seeing cool stuff, we liked sharing the sights in the night sky with others, and we've always liked our really cool equipment. You know, as you can imagine, this hobby has the coolest equipment around. Back in the 40s, 50s, and 60s, a lot of this stuff was homemade, and same today. But we've had a lot of manufacturers come on the scene, providing us with quality equipment, and the price has always been dropping, really. So it's the hobby has never been more accessible now than it has ever been. I mean, anyone can jump in the hobby and really enjoy it. You know, with the league, though, we started out small. We started out with not very many benefits. Really, the first things that the league officers did was to talk with clubs around the country and find out what they wanted, find out what they thought a new national organization could provide. One of the things that they came up with was the Reflector magazine. Back then it was called the Bulletin, and I'll show you some of that in just a few minutes. Today, though, we now have the Reflector magazine, which is a pretty sophisticated publication, I may say. We started having observing clubs back in the late 1960s. And as Chuck was just saying, I think he said over 80 today. And that's incredible. I can't talk about it because that's an hour-long conversation here to talk about the clubs in particular. But anyway, so we've grown quite a bit in that. The awards, which Chuck handles, has grown quite a bit too. Our first award structure for youth was the National Young Astronomer, started in 1993. I think that's the correct year. And we've gone on from there. So today we have 10 pathways for a young person to receive an award. We have a book service, which helps defray the cost of ordering books now. We have a library telescope program, which Chuck has talked about. We have a bunch of benefits. And it's start thinking about the league and what it is and what it can do. You know, just think about the annual meetings that the league is involved with. We have our national convention, Alcon, but we also have more regional conventions and even smaller gatherings than that, star parties and so on. The Winter Star Party is going on right now in Florida. And if you've been following that on the league Facebook page, it's been pretty interesting seeing some of the stuff that goes on there. So just think of all the stuff that the league does today to help amateur astronomy. Now, I have a slide set, which I'd like to show Terry. Show not just Terry, but everybody. Sorry, my syntax there was kind of off. Okay, let me... So here I am talking about the 75th anniversary. One person I'd like to point out, but before I go any further, is one of our members, Peggy Walker, who's put together a lot of the events and did a lot of the legwork, trying to track down stuff that we could do, and her help has been very, very much appreciated. Okay, this is a photocopy of the Astronomical League Bulletin, the very first publication of the Astronomical League, which was in, according to this, September of 1949. So this is just a front and back side. And today we're with a full color glossy magazine that's about 32 pages and written by, articles written by amateur astronomers, for amateur astronomers. So it's really interesting, and it gives a lot of good news about the hobby around the country. We have all these mini observing clubs. And with those, you normally get a nice lapel pin and a certificate suitable for framing to announce your accomplishment. We also have some other items we do for completely free. We have a system called Outreach Downloads, which gives a number of flyers that you can hand out that helps explain our hobby, helps answer questions that a lot of people have, helps you find your way around the night sky, such as this one, Navigating the Mid to Late March Night Sky, which is what's coming up next month. And this is free, and it's on our Facebook page. It will be regularly scheduled on our website when the revamp is completed with that. So keep your eyes peeled for this stuff. Library Telescope Program, as Chuck was saying, we give away up to 11 telescopes per year. We've been doing this since 2015. So there's quite a few telescopes out there now to different clubs who applied for this. encouraging for that. As I said, we're on our 75th anniversary. We have a nice lapel pin designed. We have in our top secret labs, they are cobbling this together, cranking out them by the thousands. So, and hopefully in the next couple months, we'll have these available for sale through League Sales. One more thing is League Sales. I forgot about that. Good, because I'm wearing a League Sales product right here. The old knit hat with the Astronomical League. I've tried this out personally. It keeps my head very warm when I'm out under the stars. So if you want something really cool to wear and to show your astronomical awareness, get one of these hats through League Sales. And now I'll wrap this up by talking a little bit about our media presence, which is kind of ongoing, upgrading and all that. But you can see that this is a live presentation by the Astronomical League. We also have a YouTube channel, which we've been doing, especially for the 75th year. We've been creating a lot of videos for that, placing them on the YouTube channels, videos celebrating the 75 years in some manner or other. In fact, David Levy was on it last week. I appreciate him for doing that. So this is a really big step for us to share the hobby with others, get people interested, tell people who we are and what we do. We also have a Facebook page, which a lot of this stuff will appear on the Facebook page as well. That's been going on for a couple of years. We tend to put on things like these outreach downloads with the star maps. We put on advice, how to find things in the sky. We have submissions by clubs and odds and ends that we put in about the hobby. So we're pretty excited about that to keep our presence out there and to keep people interested. Astronomical League has been around for 75 years. And from my position, I can see it being around 75 more. You know, it's the nature of our hobby is something that will always be there. People tell me about observing this, observing that, and how they failed to do this and they failed to do that. They couldn't find this, and I tell them, look, you know, it's going to be there next year. You know, give it another try. The weather may be better. Maybe you'll have a different telescope. Maybe you'll be in a different location and be able to see it. This stuff is always up there. And think of really why you're doing this. Over this past year, of course, we won't go into everything that went on this past year, but a lot of people like going under the stars and just looking up and being amazed, being in awe of what's up there, finding inner peace within themselves, trying to find comfort and satisfaction in what's above to make sense of our world. And I think a lot of people really benefit from this. So that's what the Astronomical League is all about, and the Astronomical League is here for you. Thank you, Terry, and thank you everybody for listening to me go on for probably way too long about this.
Thank you, John.
Let me see if I can get off this.
Yeah, we want to see your hat again.
Ah.
Yeah. There we go.
Well,
Yeah.
This is my other hat. This is my warm weather hat here.
Yes, you've got your summer and your winter attire there.
Always prepared.
Thank you, John. Appreciate it.
Thank you.
And I think one thing even that Scott could attest to too is what we are hearing is astronomy equipment. I know when I try to buy anything, everything seems to be sold out everywhere. I have to go on a search. Sometimes I have to wait for a month or two to get equipment. Scott, I'm sure you are seeing pretty much the same thing, aren't you, with all of the equipment sales? There's so many more people at this point involved.
Absolutely. The surge of people interested in astronomy in general because of, I think, due to the pandemic, due to the effect of people slowing down and taking time to either reconnect with their interest in astronomy or discovering astronomy for the very first time, led to an incredible explosion in people being interested in backyard stargazing. And so people decided to get a telescope, maybe binoculars. But if you just get the gear and you don't have the guide, okay, it's easy to get lost in the universe. And so with the Astronomical League's observing programs, that is going to be your That's going to be your source for learning the sky in the right way, and to gaining a deeper appreciation of what you're seeing out there. Some of these objects are very challenging to find. They're very far away, but when you do find them, to learn something about them, to understand how many million light years away they are, or what's fascinating about them, is really what enriches your knowledge of the universe that you're connected to and that you live in. And the Astronomical League's programs are second to none. They have more observing programs than any other organization in the world. And so joining up through your club or as a member at large is very, very important. So be a member and enjoy your universe in a way that otherwise you'll just be cutting yourself short.
Thank you, Scott. Appreciate that. Yeah, I know I've been trying to order different things and I'm on a waiting list sometimes. So yeah, and it helps to know there's nothing like taking a telescope out. And I've had parents come to me and say this, my child's interested in astronomy. I don't know anything about astronomy. Where do I start? I don't know what the constellations are, and there's a process you go through. And it's like Scott said, if you don't know where you're going, it makes you really cut yourself short. You need to understand what's up there and how to get to it, to look at it and then understand what is it I'm seeing. And, people look at the moon to start off with, and that's incredible because we can associate what we see with the moon. But there is so much more that is hid out there that is just fantastic. So thanks, Scott. I appreciate that.
Thank you.
One of the
all
other
of
things
you that are out there waiting for your gear, it's going to take a while because the whole industry has largely sold out of telescopes. So we're waiting like you are.
Thanks, Scott.
Thank you.
As John was saying, we are, or maybe it was Chuck, we are probably a little over 18,000 members. And of those 18,000 members, we are broken up into 10 different regions. And each region has a few states to it. So we have local chairs, or we have chairs of each region, and we have their own officers of each region. And actually, Don Knapp here tonight is the chair of the Merrel region, the Mid-East region of the Astronomical League. And I have been on the website that Don has created, and it is spectacular. Don is here to talk to you tonight about what's going on in his region, to show you some of the things. If there are more regional chairs out there, watch this. You'll be impressed with the website and everything that this region is doing. So Don, take it away.
Thanks, Terry. I'm going to share my screen, and I'm going to be bouncing around a little bit between screens I have here, but I'll start with the slideshow. Get started right here. So, if you'd asked me 5 years ago what Merrel was, I probably couldn't have given you an answer. But about 5 or 4 years ago, I started to get these emails from a fellow named Terry Trees, and he was the chair of Merrel. So I found out why Merrel was from Terry, and I met him actually, it'll be 2 years ago in July at Starquest, which I'll talk about a little bit later in my presentation, one of the large regional gatherings that we have. So best way to talk about Merrel is probably to go to the webpage that Terry mentioned. So let me do that. Can you see this on my screen? Okay, so this is the website. I created this. Our club, I'm a member of 2 clubs in the area. We're about 20 miles west of Philadelphia. And we work with a local night school to give astronomy classes in the spring. So this past spring, they said they're going to offer a website class. So I said, you know what? Merrel needs a website. So I took this class. And what you see in front of you is a direct outgrowth of the night school class that I took. So I won't spend a lot of time on it, but this is the best way to learn about Merrel. I have a home page set up, which is some quick links. All this stuff can be gotten to, but a quick link to the Astronomical League. It will open up a window. Dark sky camping. When I put this together last fall, the only one I really knew about was Cherry Springs State Park in the middle of Pennsylvania. but there are other places I've learned about getting more involved with the Merrel clubs. This will link to clubs, and this will link to the star parties I will talk about a little later. You know, I have some boilerplate things here about the Astronomical League, but this is our region: Delaware, DC, Maryland, the bottom half, New Jersey, Pennsylvania, Virginia, and West Virginia. This is right off the Astronomical League website. Membership benefits, the only one I'll point out here, I'm not going to read this to you, but down here, this is the one that is most important to me, okay? One of the benefits of being part of Merrel and the League is they're part of a local, regional, and national community, amateur astronomers. It's great to be part of a group of people that have a shared passion. So where are we? This is the Mideast region. There's only one club in Delaware. Now there's more clubs, but there's only one that's part of the AL. There's one in District Columbia. Maryland has 8 or 9 clubs, I think. Pennsylvania, about a dozen. Virginia takes the lead. The Virginia Astronomy Clubs, it's about 13 or 14. I'm starting to add club logos. Again, the website is still under construction. I built it last fall. Take a little break. I'm going to start populating a lot more things on the website. But all these societies are here. Virginia is probably the largest. Pennsylvania, second largest. I'll talk in a moment about AAAP, Astronomical League of Pittsburgh. Mention them when I go to my slideshow. Events. I'm going to be filling this up because in getting ready for this evening, I found about a lot more events than are listed here. So I'll be talking about those in a few minutes. I put resources here, stuff for kids. And in our part of Pennsylvania, we seem to have a lot of Girl Scout activity. So my wife and I took a course from the Night Sky Network and the Astronomical League of the Pacific to help us learn more about things for Girl Scouts. So I have a couple of links here that goes to the Night Sky Network and SETI. We have other things for kids, of course, observing aids, some of the typical ones, sky maps, sky and telescope. And even though maybe you can't buy stuff right now, at least there are links here to some of the major manufacturers. And I'm going to be populating this with a lot more suppliers. And I haven't got many submissions yet, but I have a spot for anyone in Merrel can submit images to me, and I will put them here. I have a number here from Delaware Valley Astronomical, amateur astronomers. They're almost a sister club in a way. 3 or 4 of the clubs in Southeast PA, we really work together on astrophotography, including the club in Delaware, and on some events. So I posted a few images from some of these folks. Nothing you haven't seen before, I'm sure. And of course, every website needs a contact page, and we have that also. So that's probably the best way I can introduce Merrel. That's our group. We're about 37 clubs. So I'm going to go one other share. We do have a Facebook page. I'm not using Facebook page a whole lot. It's mostly a way to get people to the website, but I do put some posts here. We have some people following it. It's great, and I get these sheets from John Goss, and I post them up here, and I get a few people hitting on that. They come and look at it. So, but I started out trying to do just a Facebook page for Merrel, and it's so limited that I figured I had to do a website. So, so let me go back to my PowerPoint. A few slides to share. So I have 37 clubs. And, you know, I asked for input from some of the clubs. I got some nice responses. So I think I mentioned AAAP, Amateur Astronomers of Pittsburgh, Association of Pittsburgh. That is actually the club who the previous chair, Terry Treves, was part of. And he tells me that their club was a charter member of the AL, and they hosted the first Alcon to the best of his recollection. Okay. Goddard Club, I don't know a whole lot, but this has got to be a fascinating group of people all working at Goddard Space Flight Center. Boy, if you can't have a better collection of astronomers than that, I don't know where you're going to find it. So that's a Maryland club. Novak, I got a nice response from the president of Novak. That's Northern Virginia Astronomy Club. I checked their website. It's amazing. They have over 1,000 members. That's a big club. The club I'm in, Chester County, we have about 125, which, as we've heard mentioned tonight, we're growing. 5-6 years ago, we probably were in the 60 or 70 member. We're up to 125 now. I know Delaware Valley is growing very quickly. So we're seeing it. I think Novak is seeing it also. And they host a lot of amateur astronomy events through the year. I'll talk about the Almost Heaven Star Party in a few minutes. That's down in West Virginia on Labor Day weekend. And we're hoping they do it this year, we hope. So, and they monitor multiple dark sky sites through Virginia. So they can with 1,000 members, you need to have more than one site, that's for sure. Then the Roanoke Valley, and we pretty much share the same experience here. Virtual meetings, that's what our club is, and Delaware Valley Club is doing, and Delaware Club is doing. They're seeing, RVAS is seeing increase in astrophotography. I would say the same thing for our club and the clubs in the area here. They're doing meeting on Zoom, as every club that I know of is doing them on Zoom. And we all seem to have the same idea. We have about a half hour of social time, of chit chat before a meeting, and then we do our regular meeting. We had a lot of fun at Christmas time. We had our virtual holiday party. Got the idea from John Goss of doing a limerick contest, and we had a quiz. And of course, the prizes for that were Astronomical League calendars. So that was very well received by our members. So I do want to mention Delaware Valley Amateur Astronomers as part of the pandemic. What are we doing during the pandemic? The current issue of the Reflector had a wonderful article written by 3 members of DVAA, as we refer to them, Delaware Valley Amateur Astronomers. I'm not going to go in detail here, but you can see they set up, here's Al Lamperti. He is the regional representative to the Astronomical League from Merrel. So he's an officer of Merrel. And Jan Rush is our secretary for Merrel, and she's also vice president of DVAA. So they would set up in a parking lot by a park, a municipal park. You can see they would rope off areas. They would have projectors with a number of revolution imagers or webcams taking pictures. You can almost make out Jupiter and some moons there. But they went through a couple of learning phases. Like the first time they hooked up the projector, they had an inverter, and it ran the battery of the car down in a very short amount of time. So they found they had to keep the car running. And they got a sound system, and they only allowed people there that had registered, so they controlled attendance. And when people got there, they handed out masks, they handed out hand sanitizer. So I really encourage any club that is listening, if you want to know how to do this, if you have somewhere you can do it, which is a big if, DVAA does have a place they can do it. Get the latest issue of the Reflector and read what DVAA did. They did a wonderful job. Despite having a pandemic going on, they've had, I think, 3 events now so far. Regional events, I'm going to talk about now the rest of my presentation, just a few regional events that are going on, we hope are going on in 2021. Now, NEAF, that's not in Merrell, but it's pretty close. And that is going to be virtual this year. And you never know who shows up at these places, but there's a guy that showed up. There's Scott. I'm not sure what year this is from. Okay, they let anybody in, I guess, right?
That's right.
But this is a picture I took back in 2012, and it's a wonderful event, like we've heard people talk about earlier tonight. It is like the biggest candy store for astronomers you were ever in. So when they get back, hopefully next year, to having it live, I really encourage everyone to go to it. It is, just leave your wallet locked up in the car is what I would say to do. If you want to be able to buy gas to get home. And then Novak, very active club, again, over 1,000 members. Right now they have a plan, but I haven't gotten confirmation, over Astronomy Day, May 15th. They do that in a park in Midland, Virginia, where you can see their sign, the back of their sign here. They set up and do a whole Astronomy Day event. Cherry Springs, you know, I've not actually been, my wife and I haven't been to the Cherry Springs Star Party, but we've been to Cherry Springs many times. Our club goes up along with DVAA. We tend to go up there together and set up in the field. This, if you haven't heard of Cherry Springs State Park, it's in the middle of Pennsylvania. It's right between the middle of nowhere and where the heck am I? That's where it's at. It is in the middle of nowhere, literally. And you know, a lot of times you see pictures like this and people say, well, it doesn't really look like that because it's a time lapse. Well, actually, that is just about what it looks like at Cherry Springs State Park. It is one of the darkest sites on the East Coast. They have 2 events there, June 6 to 10. And then there's one called the Black Forest Star Party, also at the state park. Usually that's in October or September. It's not scheduled at this time, but anytime there's a dark window, you'll see, maybe not this many, but you'll see quite a few folks up there, and you'll see me and my wife and people from our club up there this summer. I'm absolutely certain. We went up last summer, being very careful, not sharing eyepieces, wearing masks, and everyone's very respectful of the pandemic restrictions. But this is supposed to be a wonderful event. I hope to get there sometime. But I'll go to the park whether there's an event or not. And then we actually did go to this event in 2019. This is at Green Bank, Starquest. Again, a long-running event. It is located at the world's largest steerable radio telescope. And you can tour this thing. When my wife and I, some of us toured, we got up to this level. They had a problem with the elevator, but others got up all the way to the very tip top. And it is high. You're in a radio-free zone. Even if you turn your cell phone on, which you're not allowed to do, you wouldn't get any signal. It's a radio-free area. Even in the visitor center here, there's a cafe, but their microwave oven is in a Faraday cage. The only contact with the outside world you can get is to go into a room that is entirely lined with conductive material. I forget if it was copper or aluminum, but you're in a gigantic Faraday cage in order to access some computers to get the internet. The camping looks a little sparse. I took this on the last day as we were heading out. The field was pretty well filled up, so but there's plenty of room. And there are speakers every night. They have a wonderful raffle. My wife and I I probably put $50 into the bucket for the astronomy quilts, and we did win. Actually, won 2 of those. It's a wonderful place. The people are great there. So this is Green Bank. It's right now scheduled for July 7 to 10, and we plan to be there. The Almost Heaven Star Party. This is run by Novak, and this is actually just not that far up the road at Spruce Mountain Center in West Virginia. It's not that far from Green Bank. Another very large party. They have it over Labor Day weekend, and you can see the kind of dark sky they have and a large field. They have lectures. Here's the Novak sign. These things, I think they call it a yurt. It's where they have lectures, and they have so many people show up. They even broadcast the sound and video outside of the lecture hall. But that's a definitely bucket list place to go to also. York County Star Party, people may remember this as the Mason-Dixon Star Party. It has a different life now as York County. Unfortunately, camp canceled last year. We had plans to go. There's going to be 2 events. I think the main one is in October this year. We should be clear by then, I really hope. But this is not far from Harrisburg, Pennsylvania, near the Susquehanna. Looks like a beautiful spot to set up a big sky. Again, Novak shows up here again. This is what they call their Stargaze. This is in planned now for October, and it's a big open star party. And the last one, this is not a Merrel club, but it's in Virginia, which is part of Merrel, so I included it because it's a very large party. Staunton River Star Party, hosted by Chapel Hill in North Carolina. This looks like another big wide open field. And they have lectures and guest speakers and all those things. So it looks like a really nice event to go to also. So that's Merrel. That's any questions about it?
Well,
no.
I don't see any questions right now. I think they enjoyed your program, though.
Okay. Oh, wow, I finished just about on time too.
Yeah, Don. Thank you, Don. That is great. I know the Great Lakes region will be in touch with you about building a website. definitely.
Happy to help. Happy to help any region, any club build a website. I can help you with that. It's all menu driven. It's not that hard, but it does take some time. So
Yeah, you did a great job on that. Thank you so much for your talk. I really appreciate it. It's very interesting. And it's good to see some star parties that could possibly be coming up, because I think we're all ready to go again.
yep, we're hoping.
Yes, definitely. So, all right. Scott, why don't we do about a 10-minute break and we'll come back to
Sure.
Rachel.
Okay. All right.
Okay.
All right.
We'll
sounds
be
good.
back shortly.
Their case against Donald Trump. They documented in vivid and excruciating detail what happened on that day. A minute-by-minute account of the deadly insurrection, including never-seen-before footage of the mob invading the Capitol.
No.
we're back. Hope you had a nice little break there. And what's up next, Terry?
All right. Thank you, Scott. I would like to introduce Rachel Cionitti. She is a sophomore at the University of Kansas studying physics and astronomy. She has given 3 talks for her local astronomical group, the Astronomical Society of Kansas City. Rachel is currently on a research team studying galaxy velocities and the Hubble constants with physics and astronomy chair at KU, Hume Feldman. Rachel is looking forward to the talk about dark matter and dark energy and can't wait to share her enthusiasm with others about the beauty and mysteries of the universe. So Rachel, thank you very much for being here, and we look forward to your talk.
Hi, thank you. I'm looking forward to it, maybe the most out of anybody. As she said, hi, my name is Rachel Cionitti. I am a sophomore at the University of Kansas. I lived here before I went to this university, so I've been in the Astronomical Society of Kansas City for, I think, around 2 years at this point. And every time I get to do a talk, it's so great. So I'm just really excited to be able to do this again. I'll share my screen here. Is my audio okay? Am I loud enough
Yeah.
to the people in the Zoom? Okay,
Yes.
great. Okay, so I included both the AL and the ASKC logos in here. I'm exceptionally excited that it's the 75th anniversary. I just think that's so cool. And all of the talk prior to my presentation that I'm about to give about how enthusiastic everyone is in this club just brings me so much joy, because I think that especially in the past year, astronomy and physics and everything about the universe just brings people a lot of escapism and a lot of hope. So I hope that I can teach at least one thing to everybody listening that makes them interested and invested in this. So also, as mentioned, I am doing research with my university. So at the end, if anyone has questions about that, it's not something I'm going to talk about, but I can if anyone's curious. And finally, I am a sophomore, as it's been mentioned a couple times now. So definitely I'm no doctorate. I'm not an expert yet by any means, but I would love to share what I know. And I would love for a lot of questions to be asked, ideally, because for me, being an aspiring cosmologist, it's much more exciting to not know things than to know things. So that's also going to be the point of this presentation, is not necessarily all the answers about the universe, because we don't have many, but it's going to be very open-ended and about the things that we don't know, because that's the best time to get involved, is when the game is going and we're trying to figure things out. So we're going to be talking about dark matter and dark energy, which are 2 gigantic question marks in terms of explaining the universe. And these are ongoing things. They're not historical at all. The study of cosmology has really only been in practice and taken seriously since about the 1960s. So this is extremely new, and that's why it's so exciting. So I just wanted to include this at first. This is an illustration that's supposed to represent the whole universe in one picture, starting from the earliest thing we can see, which is the cosmic microwave background, and I'll talk about that, all the way up to our solar system. Obviously not to scale. We may feel like we're that big in the universe, but we're not. This image goes logarithmically in scale, so each little bit is an order of magnitude smaller. But I just think this image is really cool, because I think everyone listening right now is here because we're all in awe of the universe and how beautiful it is. So I figured it had to start out on this note. But we're going to go over all the things that we can't see in this image specifically. Dark energy and dark matter are both called dark because when we're looking at this image, we can't see them at all. And we'll get into what that means. So we're going to start out chronologically with the title, with dark matter. So your first question might just be, what is it? And I can't answer that question. No one on the planet can yet, but we do have a lot of good ideas and we do know that it's there. So there is a difference between knowing what it is and knowing that it's there, the same way that in the dark, you might be able to hear someone is in the room, but you can't see them. So that's exactly what's going on with dark matter. But it's not like a person speaking to us. It's not that obvious. So how do we know that it's there? we're going to learn about that. We're going to learn about the first time that dark matter was sort of discovered. And though it wasn't called that at the time, it was technically the first observation. But first off, let's talk about what it means when we say there's matter that we can't see. It sounds really counterintuitive because everything we see is matter. Everything is visible. And the universe is partially made up of that stuff. It's actually not entirely, and that's the point of dark matter. The stuff we can see, the stuff that I'm made of, and the stuff that your computer screen is made of, is called luminous mass, which means that it's protons, neutrons, atoms, and these particles interact with light. So when photons hit it, or pieces of light hit it, it reflects that light back and makes itself visible, as opposed to something invisible where the light just goes straight through and you can't see that there's anything there. So when we talk about luminous mass, we're talking about the stuff on the periodic table, and when we're talking about dark matter, it's a little more apt to call it invisible matter, but we named it and got stuck with the name. Happens a lot in astronomy, so we call it dark matter. So we see effects of it, even though it's not luminous. So this is the unknown stuff, is dark matter. And it's just a title for, it's almost a placeholder for, we know something's there, but we can't explain it yet. So it's a very new, very developing field. And the image to the right is from the Millennium simulation, which is a simulation of dark matter. So it's made visible just for us to comprehend. But this is what the structure of dark matter looks like on the largest scales of the universe. It looks like filaments in this way, the way that it's distributed, as opposed to normal mass where we see a lot of it in stars or in objects. Dark matter is distributed in this way. And matter on large scales actually is distributed in this way too. It follows this sort of as a map, but we'll talk about that as this goes on. But essentially this gives you a visual idea of what truly isn't visual. And I was impartial to using a Millennium simulation picture because I've worked with small parts of the simulation before. So it's really cool. But we're talking about this, but how do we actually know it? As I said, we're going to talk about how it was discovered, and this was done in the 1930s. So we're talking about one methodology, while in the present, it's been confirmed with many other methodologies, but I thought it would be best to start out with the first one that happened so we can discover it the same way that astronomers did in the 1930s. So we talk about this missing mass, we can't see it, but we see its effects. But what does that really mean? How do we do that? Well, there's essentially 3 steps. The first step is to measure mass that's present by observing how interstellar objects move around, how they behave, how they're influenced by their surroundings. So that's measuring more acting mass than mass that you can see. The second step is to measure how much mass you can see, not measuring effects or anything indirect that way, but just looking, saying, I see this many objects, they weigh this much, add it all together, that's how much mass there is. And 3, you compare. And up until we discovered dark matter, we expected these things to be the same because why wouldn't they? Why would there be some weird imaginary matter pervading the cosmos for no reason that we couldn't see? We hadn't even thought of it. But we're going to go through these 3 steps and see what happened and what was discovered. So first of all, we're going to measure the mass in this indirect way where we conclude a mass of a galaxy cluster, that's going to be our subject, which is a big group of galaxies gravitationally bound together, sort of like bees around a beehive. That's a way to picture a galaxy cluster. We're going to measure the mass of that galaxy cluster, not by just adding up all the galaxies as weights, but by how they're acting. But how do you do that? That doesn't really make intuitive sense. To understand this, I'm going to go over some basic ideas first, because you never know who's listening, and it's always valid to not know. It's always much better to not know and admit that you don't know. So we're going to go over some basics. The basic number 1 is mass and matter aren't the same thing. You might hear them used interchangeably, but they're not quite. Mass is just the quality of having a gravitational pull or curving space-time into a well. But matter is, it has mass, but it also is, in the way that we think of luminous mass or matter that we can see. So on the left, you can imagine that yellow ball is the sun with its gravitational pull curving space-time and making things orbit around it. So that is matter and it has mass. But to the right, there's mass there, but there's not necessarily any matter. So when we talk about measuring the mass without just counting how much weight of stuff there is, we're talking about the thing on the right. Basic number 2 is that mass and matter consequently create an inward force, which is that curve in space-time that I'm talking about. So think of a trampoline. It's a very basic example. If you have a trampoline and you put a bowling ball in the middle, and then you drop a marble or you roll a marble at the edge, it will go in towards the center and fall towards the bowling ball because the bowling ball has a lot of mass. So it's creating an inward force that attracts other objects with matter and mass. So objects in space are the same way, as you can see in the picture to the right. And the more mass you have, the more pull you have on other objects with mass. Basic number 3 is that motion creates an outward force. So if we think about the marble again, if you just drop it very gently, it'll go straight towards the bowling ball. But if you roll it with a bit of force, it might go around in some circles before it gives way to the bowling ball's attractive force. So motion basically, in the context we're talking, is the antagonistic force to gravitational pull. The more velocity something has going around a massive object, the more ability it has to fly away instead of falling towards the center. So we have these basic ideas, but how do we combine them in order to do what we were talking about and measure the mass of a galaxy cluster? Well, first let's think of something much more simple, because this is always what you should do in physics, is start with a very simple model to understand, because that's always very effective. Something you can think about, as opposed to a big complicated galaxy cluster, is a ball on a string. So imagine you have a certain type of string of a material, and then you have a ball that you're using continuously, the same ball. And you spin around in a circle like this. And say your string is too weak and it breaks, it snaps, and the ball flies away out of the orbit. Well, you didn't successfully hold the ball in because the attractive force holding it in this loop wasn't strong enough. So then you switch to a stronger string and maybe it breaks again, and then you switch to a stronger string, and finally it holds the ball in that orbit. So you can figure out, based on how the ball is moving, how strong your string needs to be, or the qualities of the ball tell you how strong your string needs to be in order to keep it in. So you say, okay, the string has to be at least this strong, if not more strong, to make this system work. And in a sense, that's exactly the way that the galaxy clusters are, except the galaxies represent a ball, and the inward force of their mutual mass is like the string. So we can't look and see the string, but we can see a bunch of galaxies and how they're acting, specifically their velocities. And we said how the velocity is the antagonistic force to the string or the gravitational pull. So we look at a galaxy cluster, we look at the galaxies, we say, okay, on average, they're moving this fast, which means that in that cluster, there has to be at least this much mass to hold them together in this cluster. Otherwise, they would fly apart and there wouldn't be a cluster at all because their mutual mass wouldn't hold them in. So this is how we can calculate indirectly how much mass there has to be in a galaxy cluster, because otherwise we wouldn't see a galaxy cluster at all. So that is how to do that first step. You find the outward force, which you can observe by measuring galaxy velocities. And if anyone is curious as to how you do that, I will kind of mention a tangential thing later, but if anyone's curious, totally ask. In a short way, it's done by using redshift, which indicates how fast the galaxy is moving. Typically away from you, typically things are redshifted for reasons we will get to, spoiler alert. But also things can be blue shifted if they're moving towards you, and the amount that they look reddish or bluish tells you how fast they're moving. So once you know how fast they're moving in general, you know how much mass there has to be in that cluster. So you've gotten your cluster, you've figured out how much mass it has, write it down. And now we move on to the second step, which is measure how much mass you can actually see. So we're not using as complicated a math here, we're just saying, okay, we see this much light, how much stuff is there? And this is quite simple when you do it in a rudimentary sense, because there's a direct relationship, or a very good relationship, between mass and luminosity for main sequence stars, which comprise a lot of the stars in the universe. So you can see a linear relationship here, which just means that if you see something with your telescope that's, say, 1,000 solar luminosities, or 1,000 times the brightness of the sun, you just use this graph and say, okay, it's about 10 solar masses. And so you can look at your galaxy cluster, collect all of its light, and say, okay, it's about this bright, so it should have about this much mass. And for the purpose of what we're doing, you can make a pretty darn good guess with that method. So you write down your second thing. You write down, okay, we used our telescope, optically we analyzed it, and this is how much mass there should be. And the final thing you do is you compare them, because they should be the same, right? Except they're not. And actually, they're very drastically different. The first result tells you that you need way more mass than you're seeing optically, or when you look at the galaxy and you collect the light, you're only seeing a tiny bit of mass compared to what you know, according to the laws of physics, needs to be present in order to make that galaxy cluster exist. But the issue is we don't know where this mass is coming from because we can't see it. We were literally blindsided by this when we discovered this. So this is exactly the methodology that was used by Fritz Zwicky in 1933. Very simplified, obviously, but he did basically the same thing with a specific cluster called the Comet cluster. So he did what we did. He measured the mass and then the luminous matter, and he was like, wow, those are not the same at all. What is going on? And his specific results found that there was a discrepancy by a factor of 50 times, as in there was 50 times more stuff that needed to be there as compared to what we saw. So this poses a huge issue. And this is technically the first observation of dark matter, although at the time, people didn't really pay attention to it. For some reason, it just didn't come to the fore in astronomy quite yet. And then there are multiple other ways of figuring out that dark matter needs to exist that come decades later, but this was truly the first discovery. So there's a lot more that we know today. One of the most important things that we know is that dark matter exists everywhere and in galaxies, not just in galaxy clusters, because there was no reason for them to assume that it was everywhere when they first discovered it in those clusters. Maybe they thought it was something unique to clusters. And the sort of medium in clusters. But no, it exists everywhere in that filamentary sort of way we talked about. And so it exists in galaxies. And namely, it's actually extremely important to galaxy formation. Without cold dark matter, spoiler, without dark matter, we wouldn't have galaxies in the way that we have them. We wouldn't have galaxies arguably at all. Because dark matter settled into that filamentary structure before luminous matter, or the matter we exist in, fell into structure at all. And basically, regular matter has to fall into a gravitationally bound structure in order to create things like stars and create things like galaxies and planets and things for us to exist on. And the only reason luminous matter was able to do that is because dark matter did it first and then attracted luminous matter into itself. To build that structure. And we know it exists in galaxies because of, as I mentioned, a discovery that came decades later about galaxy rotation curves, which essentially is this plot here, which means that when you have a galaxy, most of the mass is concentrated at the center, and it gets less so intense as you move out towards the edges of the galaxy. Think a spiral galaxy, one that's spinning around its center. So essentially, when you have less mass, you have less of that attractive force that we were talking about. So things that are at the edge are not going to be moving as fast because they're not as tightly bound to this attractive force in the center. So what you would expect is the further away you move from the center of a galaxy, the slower objects are going to move. But what we eventually found out is that that's not true. When we look at spiral galaxies, it reaches a certain velocity, and then as you move away from the center and move away from that attractive big piece of mass, it's not slowing down. It's acting as though it's much closer to the central mass than it is, which also indicates a strange occurrence, a problem, the same way that we found in the clusters. Because essentially what this is implying is that there's more mass present, there's more pulling force making things go faster than we see. So it's sort of the same issue. And our own Milky Way that we're sitting in right now is 95% dark matter. And we think that dark matter in spiral galaxies exists in this sort of spheroidal halo shape. What we also know is that we know it's probably non-baryonic, which is a fancy way of saying that it's not made of protons and neutrons. A couple of reasons we know this are, for one, we would have noticed backlit areas, which means that if dark matter is just regular matter like us, that we're made out of, we would have seen at this point it backlit, which means that in the dark, once again, we're going to use an example of having a friend in the dark. If they shine a flashlight at an object behind it towards you, you can't see the object, but you can see a silhouette. So if dark matter was made of the stuff we're made of, or the stuff of whatever your friend is holding and shining a flashlight behind, we would see a silhouette, but we don't, which indicates to us that light doesn't go around it, it goes through it. And also, when I say not enough elements in the slide, what I mean is that particle physics was able to predict with very good accuracy, based on a lot of things we already know about physics, how much of each element there should be in the universe. And it was truly very accurate, as in there's about 75% hydrogen and 25% helium. So if we were to suddenly say, oh, there's like 50 times more matter here, then you would suddenly have a huge issue with the ratio of the elements, because that doesn't quite add up with particle physics. So there are two very compelling reasons why it's probably non-baryonic, which means a different type of particle than we're used to. We also know, as I spoiled earlier, that dark matter is agreed upon as being cold, which essentially means that it's slightly more dense than the regular matter that we're used to. And what this means, as I said earlier, when I said that it dictates large-scale universe structure of regular matter, is that in the early universe, it was very hot. The early universe was very active, very hot. Particles were whizzing around, particles of matter and dark matter. And when things are whizzing around and they have a lot of heat, they don't cool down and calm down enough to coalesce into a gas cloud and then a star and then a galaxy. Objects can't form if things are too energetic. So when it was hot like this, dark matter, since it's more dense and it's cold, quote unquote, which essentially means it's affected less by the radiation, it's not affected at all by radiation because light goes straight through it. It was able to calm down in this very radiative environment and settle. And it settled into this structure, and the universe was smaller back then, but it still wrote this sort of mold into the universe that has stuck as it's grown. And as we talked about how areas of mass attract more mass, even though the matter that we're made of was whizzing around at this point, eventually it calmed down enough to fall into these areas of higher mass of dark matter. So dark matter was sort of telling, and is still telling, luminous matter where to fall gravitationally. And this governed galaxy formation. It provides a very good theory of why galaxies form the way they do, because they're forming according to this filamentary structure. What we don't know today is what it actually is. We know that we call it something, but we can't say exactly what it's made of. There have been a few options proposed, some much more favored by scientists than others, and it's constantly changing in terms of like specifics. But a few of the options that have been proposed are machos. Cosmology is great with acronyms. It stands for Massive Compact Halo Objects. This was proposed by people who disagreed with the majority and said that maybe it is baryonic, or maybe it is made of regular matter. And when we see that halo structure of stuff around a galaxy, maybe it's just a bunch of matter objects that don't give off light, such as red dwarfs, which you can see here, or sorry, brown dwarfs, which are objects that almost became stars, but then they didn't. So they're just big pieces of mass that aren't giving off light because they never started undergoing fusion as a star does. And another type of object is very, very small black holes. That sort of, when you add them all up, they would create a large amount of mass contributing to what we're seeing. But as we said, we can reasonably say that it's probably not those because we would have seen them backlit by now. So not many people are in favor of this theory at this point. Another theory, introducing another great acronym, is either WIMPs or axions. WIMP stands for Weakly Interacting Massive Particle, which essentially means that it interacts gravitationally but not with light, the same way that we saw that image of a gravity well without anything we could see sitting inside of it. And another option is axions. And these are both hypothetical particles that are sort of what people think of when you say dark matter. You think of a particle that is invisible. And neither of these particles have been directly discovered yet, but specifically axions have been theorized by particle physics to solve other problems that have nothing to do with cosmology. So basically, people have a lot of faith in these because there are two different areas of science, one being cosmology saying, we need a new type of particle, and particle physics saying, we also need a new type of particle. So people are searching for these because that seems quite compelling, that two separate areas are sort of looking for the same thing based on theories. And the final option is somewhat still popular, but it's not nearly as popular as the particle sort of idea. It's called modified Newtonian dynamics. Everything we've talked about has to do with ideas of gravity and mass. And those are based off of Newton, basically, the guy that said, why does an apple fall from a tree, or allegedly said. So some people think that theories of gravity are actually what need to be amended, that there's not a new thing, but just our understanding of physics isn't quite right. And it's always good to have people saying things like that in cosmology, because you should never get too attached to one idea. You should always keep your mind open that you're doing something wrong. But in general, based off of a lot of evidence we've had, a lot of which I've mentioned, people do think that the particle argument is the most compelling, because MOND is a little finicky in terms of describing when it acts the way we expect and when it breaks down and starts acting differently, and why it would do that at that certain point. For example, trying to determine why the center of a spiral galaxy acts the way that we expect with traditional Newton, but somewhere along the way to the edge, it would change. So the most popular theory is the particle idea. And that's why there's a lot of searches going on for them right now. Here's a map of a few underground detectors, which essentially the idea of those, when you're looking for dark matter, is these detectors are underground because they're avoiding interference from cosmic rays, which are energized particles coming down onto Earth's surface from space. So they go underground to avoid this interference, avoid these particles that are hitting everything that they're trying to look at. And they're just huge vats of liquid, liquid that have a lot of sensors around them, so they can look and see on the very small scales what's going on. Because the idea is, if we're looking for one of these particles, eventually just one has got to move and got to hit one atom in that liquid, and it will impart some momentum onto this particle and make it glow a little bit, because you're giving it energy, basically. You're giving it heat in that collision. So these huge containers are built with tiny sensors looking at all of the atoms in hopes that they will see one of those indications, that light flash that indicates a hit. But the tricky thing is, as I mentioned, they're built underground to avoid cosmic rays, which are other types of particles that would do the same thing, but we know what those are, so we don't want them. We want to be able to single out the dark matter. It can still be complicated because there are still particles that can get underground and give those signals. But the search for dark matter is very intense because it seems very ripe for a huge discovery. So that's why there are so many. And I even think this map is a little bit old. I think there are probably more now. But essentially, that's one way to search for them. And another way to search for them, since we mentioned that they're hypothetical particles proposed by particle physics in an isolated way, is that we can look for them in particle colliders by trying to collide particles and see if those ultra fast speed of light, almost speed of light collisions create these particles in the products. So that's another way that we can look for dark matter. So those are the two basic ways that people are searching, and people are searching. It's very fervent, very active, very exciting. One of my personal goals is to go see one of these. So essentially that's dark matter, and that's where we stand currently. And what we found out is that 22% of the universe, or about, is dark matter, and only 4% of matter in the universe is our matter, our regular matter. So that was a shock to find out, as we mentioned before, that dark matter drastically outweighs regular matter. But when we look at the universe pie chart as a whole like this, there's something else that's actually taking up 74% that isn't dark matter. And that's where dark energy comes in. And the 74 number is a little dubious at this current point, but for now it'll do. It gives you the general idea. We'll talk about why the 74 is a little dubious. But now we're moving on to the second half of why we don't understand anything that's going on in the universe, and why we're trying our best to, is dark energy. And you may be thinking, this is a little bit strange. You were talking about things, even if it's something we can't see, you were talking about things and objects in a way that we're familiar with? How is it that the universe is comprised of just energy? And the only thing I'd like to bring up here, I try not to include equations, but I hope this one is acceptable. E equals mc squared, which essentially means energy equals mass times the speed of light squared, which means that energy and mass are kind of the same thing. They can interchange between each other if you give mass a lot of energy, or a lot of speed, I'm sorry. So essentially, energy and mass on either side of this equal sign can sort of be like the same thing. So if it sounds a little strange when we say that 74% of the universe is energy, which you typically think of as intangible and sort of just very separate, that's something that you kind of have to get used to wrapping your head around. But essentially, 74% of the universe around that is dark energy. So if we're going to talk about dark energy, let's talk a little bit first about just ideas of the universe as a whole. Because dark energy has to do with studying the universe on its largest scale, which can lead to questions like, is the universe finite? Is it infinite? Is it expanding? Is it contracting? Is it staying the same size? Dark energy dictates our answers to these questions. So let's go over what some people thought before we knew anything about dark energy. The first thing is the Greeks. The Greeks argued that the universe was finite, which means that it's a certain size and it has a boundary and it's not changing size, because they said they saw a bunch of stars in the sky, probably much more than us because darn light pollution, but they saw a bunch of stars in the sky and they said if the universe was infinite, there would be infinite amount of stars. So the sky would just be white. It would be full of stars in every possible place. So they said the universe must be finite. Isaac Newton, who, as we've mentioned many times, is an expert on gravity, said if it's a closed container and there's a bunch of stuff, a bunch of mass on the inside with gravitational pull, it would pull in on itself and it would make itself collapse. And luckily, we haven't experienced that yet, hopefully won't. But so that propelled him to say that the universe must be infinite, because otherwise it would be collapsing on itself and structure wouldn't have been able to really form. And by the time Albert Einstein was thinking about the universe as a whole, what people knew is that, first of all, if there were infinite stars, we wouldn't see the sky fully lit up, because stars get dimmer the farther away they are, the same way that headlights don't hurt your eyes from a mile away as they do in your face. So there could be infinite stars, and we still wouldn't have that bright sky the Greeks thought of. And also they're dimmed by things like interstellar gas and dust. But what Einstein and his colleagues usually thought is that the universe was in a steady state, which just means it exists. It's basically a certain size, if you want to put it that way. It's not growing, it's not shrinking, it's just there. And that's what a lot of his colleagues thought, and that quickly got turned on its head in 1929 by Edwin Hubble, because Edwin Hubble discovered, first of all, not only that the universe is more than just our galaxy, because if we can take a little sidetrack, up until this point, people thought that the Milky Way was the entire universe. And of course, now we know that there's so many other galaxies that we can't even fathom it. But people thought the universe was a whole lot smaller up until Edwin Hubble discovered that the universe is bigger than our galaxy by finding a way to calculate distance and saying, holy heck, the math is telling me that this thing I'm looking at that I thought was really close to us is really far away. And then he found a bunch of things like that. And he said, okay, the universe is much bigger than we thought. And along with this discovery and along with the methodology he used to deduce that there are other galaxies, he figured out that the universe is expanding constantly. And this led to the idea that was actually partially credited to, his name is French, I think it's like Georges Lemaitre. He was a Catholic priest and he contributed to this idea of a Big Bang because he and others thought that if the universe was expanding constantly, that means that if it was this big one day and then the next day it expands some and it was this big, then that means that yesterday it was smaller, and that means that the day before that it was even smaller. And you can just take that to the logical extreme and say, okay, at one point it would have just been infinitely small, or it would have been very, very small. And he was actually initially, because we hear about this so often today, the Big Bang Theory, but he was actually rejected for it initially because people thought that he was just a Catholic priest trying to insert a Genesis context into the universe. And astronomers were like, no, 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 we won't have that, which I think is really interesting because it turned out that this is the most compelling idea. But we'll talk about how Edwin Hubble figured out that the universe is expanding, because I'm sure you're wondering that. It's not intuitive at all. And especially these two people, Vestal Slipher and Henrietta Leavitt, are very important to this discovery that Edwin Hubble made. So Vestal Slipher and Henrietta Leavitt both essentially were astronomers that created powerful tools that Edwin Hubble could use in this discovery. The first one is by Vestal Slipher, who realized a relationship between redshift and blueshift of objects and their velocity. So essentially, if you look at an object in the sky, you can collect its light. And in a very simple way, objects have a spectrum, and they usually have a line in that spectrum, stellar objects, that say, just imagine it in the middle. So there's a light spectrum and there's this black line in the middle. And when you take the spectrum from that object and you separate out its visible light into the spectrum, this line might be moved to either the left or the right, as in the red end of the spectrum or the blue end of the spectrum, depending on its motion. And if anyone's curious about the specifics of that, I can go into it. But essentially, when you look at an object and it seems reddish or bluish, that can tell you reddish, it's moving away, and bluish, it's moving towards you, because this is called the Doppler shift. And it's the same rule that governs why when trains come towards you, they sound like they're increasing in pitch. The train horn sounds like it's going up, and as it's going away, it decreases in pitch. Maybe a car horn is a better example. I don't know how often people use trains nowadays, but you get the idea. So that happens with sound waves, because when it's moving towards you, the train, which is emitting the sound wave, is crushing against the sound wave as it's traveling and basically squishing it on its way to you. But then as it's moving away and it's emitting this light, it's moving away and the light catches up a little bit, the sound wave, which stretches it out a little bit. So when the sound wave is squashed, it sounds higher because it has a higher frequency, in a shorter wavelength. And when it's moving away, it has a lower frequency, so it sounds lower. And if you can imagine that, then you understand what's going on here. It's the same exact thing, but with light. And this is extremely powerful because when you look up at objects in the sky, you can't see them moving. They're too far away, it would take too long. It's not feasible. You can't just look and see a star moving across the sky if it's too far away. So this is an extremely powerful tool. It's completely essential to all astronomy. And the next tool was found by Henrietta Leavitt, and it indicates distance. And this is also just extremely, extremely important to everything that we know. Hubble would not have been able to do what he had done without Henrietta Leavitt's discovery of what are called Cepheid stars, which essentially means they're stars where the period and the luminosity is related. And when you're calculating what this is important for, which is distance, the two things you need, or I guess the one thing you need, is you look at an object and you figure out how bright it is, regardless of how far away it is from you. Not how bright it is, and maybe it's dim and that makes you think, oh, it's far away, but how bright it is on a non-relative way. So it's absolute brightness. And when you know it's absolute brightness, you can compare it to how bright it looks to you. So say you know how bright a flashlight is, and then you're seeing it far away from you and it's dim, that can give you an idea of about how far away the flashlight is. So if you find an object in the sky and you know how bright it would be if it was right on your face, and you say, okay, it's this dim, that gives you an idea of how far away it is. And this is just so incredibly important. And that's hard to usually do because when you look at an object, you don't really know how bright it would be if it was right in your face. You have no way of knowing. So when you look at a star, you might say it's bright and it's far away, or it's dim and it's close. Prior to this, it was really hard to tell the difference unless something was very close to us. So this gave us an ability to measure distances to things that were far away. Because if we could find one of these stars, essentially what a Cepheid is it increases and decreases in brightness periodically. So say it's going like this and it's getting bright and dim and bright and dim. However fast it's doing this tells you about its absolute brightness. So you can see here that the X scale is how long it takes for it to go through one of those bright, dark, bright cycles. And then the Y-axis will tell you its luminosity. So this is just an extremely powerful tool because now we can know distances so long as we find one of these special stars that goes bright and dark and bright and dark. So Edwin Hubble, using these two methods, realized that there's a linear relationship between velocity and distance of objects. Specifically, he was able to find distance to a bunch of things using those stars, and then he assessed their redshifts, and he plotted them against each other and found that it's always true, or almost always true, that the farther away something is, the more it's redshifted. And remember that when something is reddish, that means it's moving away. And the more red it is, the faster it's moving. So the further away something is, it's more redshifted, which means that it's moving away faster. And this is essentially how we deduce that the universe is expanding in all directions at once. You may think that this indicates, oh, why is everything moving away from the Earth? Why is the Earth special? Why is everything receding away from us? But actually, that's just how it appears, because the universe is expanding in all places at once. And a good way to visualize this, a metaphor that I wish I could take credit for, is raisin bread that's cooking in the oven. So when you have raisin bread like this, think of the bread as space and the raisins as galaxies. So you put this in the oven and it starts cooking, and the bread will rise everywhere all at once, just like space is. And these two galaxies will separate, and these two galaxies will separate. And these two galaxies will separate, and these two galaxies will separate. And you can think about it this way, that every galaxy in this bread, or in this space, every raisin in this bread, I better keep the two straight, they think that everything is moving away from it. To each of these raisins, it looks like all the other raisins are moving away from their perspective. So it's not that we found out that everything is especially receding from the Earth for some reason, but it's just how it appears due to the fact that this expansion is everywhere all at once. And so that's also why more distant things look like they have a greater recessional velocity. Because if we think about these two pairs of galaxies, say that the center one is the one we're looking at. So these two galaxies are close, they're 5 centimeters apart. These two galaxies are farther, they're 10. And say over 2 seconds, we're here, which is very fast cooking bread. We've made very special bread. But say over 2 seconds, it's grown this much. So this has gone from 5 centimeters to 10 centimeters, which is a change of 5 centimeters for 2 seconds, which means that it's 2.5 centimeters per second. That's the velocity of this one, according to the one in the middle. But to the one on the right that was more distant initially, it's gone from 10 centimeters to 20 centimeters, which means it changed 10 centimeters over those same 2 seconds, which means that that's a difference of 5 centimeters per second, not 2.5. So to the raisin in the middle, it looks like this one is moving away with a greater velocity, even though it's doing the same exact thing the one to the left did. So when we look at this plot, it says things that are farther away will look like they're moving away faster for this reason, even though it's not a true velocity, but just a consequence of the space in between growing. So this raisin bread is a lot like the universe, which is very important. I think that this analogy is very elucidating. So moving on in our story of dark energy, because it's far from done, in some ways it's only getting started, is in 1998, which is many, many years later, two teams realized that the universe is expanding, as we already knew, but it's expanding at an accelerating rate, which essentially means if you think about the raisin bread, the bread wouldn't be rising at a constant rate, but as time goes on, it would rise faster and faster. And this was a crazy discovery. And we can talk about why. Why is this a crazy discovery? Is that intuitive? Is it intuitive that the universe's expansion should be speeding up? And for reasons that we talked about, no, it's not quite intuitive, because the universe is holding a bunch of mass, which even if the universe is growing, the mass is exerting that force that's pulling it in on itself that Isaac Newton had mentioned. So if it's expanding, that energy should be decreasing over time and yielding to the mass that's in the center. So how is it speeding up? It's gaining energy from nowhere. It seems to violate the conservation of energy, which is essentially the idea that you can't create new energy. You can turn mass into energy, but you can't create new energy out of nothing. So this seems to violate that principle because it's getting faster over time for virtually no reason. So this was a very crazy discovery. And as I said, 1998, that's incredibly recent. So essentially what people thought before, once they finally admitted that Einstein and his colleagues were wrong and okay, we have to accept the universe is expanding, they were comfortable for a few years, but then they got thrown a curveball again by discovering that it's accelerating. So what people thought before is that the universe is expanding, but it's slowing down because the energy should be decreasing and the matter should be pulling the universe in on itself. What people know now is that it's expanding, but it's speeding up for some unknown reason. So something is fighting against gravity, but we don't know what it is. And that is dubbed dark energy. Dark energy is whatever is propelling the universe to fight gravity in this way. And dark energy, especially since it's so incredibly young, is even more poorly understood. We have less of an idea of what it may be, but that's why it's so exciting to learn about now, because you can try to get involved in the process to figuring out what's going on. The leading theory is that it is a property of empty space, or an intrinsic energy of space, which essentially means that space itself has energy, and the reason it would increase is because we talked about how space is introducing more space. So if space has an intrinsic energy, say you have this much space, it'll have a certain amount of intrinsic energy, but this intrinsic energy will drive it to get bigger. But now that it's gotten bigger, there's more space, so there's more space expanding stuff. So it's like a feedback loop. Space wants to make itself expand, so the more space there is, the more it's going to expand. So that's the general idea for why it is speeding up. But the mechanism as to exactly what this energy of space is and how it's going on is what people are trying to figure out. And specifically, as I mentioned quite a bit ago when I said that 74% of the universe is dark energy, that's actually currently very in tension. There were even recent discoveries, like every day actually, probably, that are influencing this tension. It seems like it's not going away. And the tension that I'm talking about is that there are two methods for discovering dark energy that I won't get into in detail. The pictures show a little bit of the detail, but essentially you can think of it as there's one way of calculating how much dark energy is contributing to this expansion, where you look at the nearer part of the universe and you use that to make your calculations. And then there's another way where you look at the very distant universe to make your calculations. And they should give you the same value. Energy of space should be sort of a constant thing throughout space. Even though space is speeding up, the thing that's making it speed up shouldn't change. But what we're finding is that when we use these two methods of measuring how much dark energy there is and how strong it is, basically, that's what these numbers represent, we're finding very different values that are not overlapping. One group using the nearby method is finding that dark energy is 74% of the universe, and the other is finding that it's about 67%. And they may sound close enough to you, but in cosmology, this is actually a really big problem. At a recent conference about this, someone that is essential to the study of dark energy, Adam Rice, I believe his first name is Adam, said basically that we are in a crisis about the value of dark energy and how much it's contributing to the universe. But as I've said before, to cosmologists, that's incredibly exciting because that means that we can all try our best to reconcile it and figure it out. And if anyone wants me to go into details about these two methods and how they differ, I can do that if anyone asks. So this is another picture representing actually the three different values. These two are more long-standing, and there's a clear distinction between one of them is a near method, one of them is a far method. But there are three values now that are competing, which makes it even more of a mess, which is even more exciting. But there is a third method that has came out extremely recently. I think this lines up to 2019 for their most recent measurement, where they say that it's 70, which is right square in the middle of these two. And the error bars don't overlap. So that creates another problem. So this is dark energy right now. We're in the thick of it. We're definitely in the beginning stages of understanding what this is. And again, as there was with dark matter, there are people who think maybe we just need new physics. Maybe there's not an intrinsic energy of space, but maybe we're just fundamentally misunderstanding something. Other people think that maybe one or two of these methods are just prone to having errors in their data, and maybe that's why we're getting wrong measurements. Some people think that dark energy maybe isn't constant over the universe, but maybe as time goes on, that energy of space gets stronger, gets weaker, and it can change. All of these are not necessarily off the table because this is so incredibly new and ongoing. So essentially, that's dark matter, which has a lot more questions than it has answers, even compared to dark matter. But we arrive at this model, which is the lambda CDM model. And the lambda stands for essentially dark energy, and CDM stands for cold dark matter and matter, which is our regular matter that we're made of. And this little piece of text, this symbol, represents what we feel like we currently know, which is very subject to change, always is. But this is essentially generally an overview of the theory of modern cosmology in terms of where we stand. And I thought I would add this picture again just to wrap it all up. But any question?
Wow. Yes, there are some questions.
Okay.
Cameron Gillis is asking, is there a theory that for the effect of dark matter, or that the effect of dark matter is the effect of the folded fabric of space?
Oh, geez, that's beyond my pay grade.
Okay.
I think that there are definitely a lot of theories like that that are more fringe theories, but I mostly have studied the mainstream ones, so
Okay.
I couldn't speak to the validity of that, but I think it's definitely worth looking into because everything in cosmology sounds ridiculous if you think about it too much, so it's at least worth a shot at studying.
Okay. There's another question. What is the latest theories on white holes?
On white holes?
White holes.
From my understanding, those are the corollary to black holes, I think, where people think that there's an immense amount of like matter receding from them. I don't know anything about it personally, but I would say just from my intuition that I feel like we would have observed that unless people think that they're in other dimensions, which actually is something I think that comes up as an issue when we're talking about things like dark matter and dark energy.
Sure.
But yeah, I don't personally know about that.
Okay. Gabriel wants to know, can general relativity actually explain dark matter?
So I'm not really sure. I think that the particles that are being theorized as very likely candidates for dark matter fit within what we understand of quantum mechanics, but there is tension between relativity and quantum mechanics that is still sort of an issue that wasn't brought up here, but I think that also sort of is integrated into this whole pantheon of issues. But that's something that I don't know much about either. I gotta remember all these so I can look them up myself.
Right. Harold Locke wants to know, what amount of dark matter has been collected so far in these underground collection bins?
So we haven't actually found something yet that we can definitively say is a dark matter particle. We have had very recent developments in an observatory in Italy. I can't remember its name, but I think in 2019 there was something published from them where they thought they found an axion, which would be a good candidate for a dark matter particle. But those things have to go under rigorous review and for a very long time, and other people have to discover them. So I believe there's at least one thing on the table, if it hasn't yet been disproven, that may be one single dark matter particle that we found, but we'll have to wait until people at other observatories maybe see something similar or their data is finalized. But as of yet, we have nothing that we can point at and say, we found you, dark matter. But when it happens, it'll be super exciting. So,
Chris Larson says, I've heard the train horn analogy several times now. This is the first time I understand it in relation to light and measuring the distance of stars.
That's great.
A lot of people are, they really love the way that you have explained some pretty complicated concepts here. So
that's great.
Yeah. Let's see. People are saying that you're making their minds expand here.
That's great. That's the goal.
Let's see.
These questions are making my
excellent presentation. I mean, people loved your presentation.
Thank you very much.
Let's see.
You know, if some random sophomore can learn all this, you guys can too.
Yeah. Well, you're not some random sophomore. Christy White says she did an excellent job of explaining this. Even I understood her. So
That's great.
I think it's wonderful. You know, really a mark of intelligence is the ability to explain something that's very complicated so that almost anyone can understand. And that is also a mark that you have a good understanding yourself. So
Thank you.
Thank you, Rachel. Just following that line of thought, I need to read you just a couple comments that are here. This is making sense. Something must be wrong. This is great. Rachel is very clear. I enjoyed it. Clearly, everybody has enjoyed your talk. Thank you so much. We will have to have you come back again. It has been a lot of fun, very educational for all of us, I'm sure. And I greatly appreciate you being here as everybody else does.
Of course. It's what I love to do. So.
Oh, well, yeah, you can tell. Enthusiasm always has a way of showing up when somebody really enjoys what they're doing. So thank you very much. Really appreciate it.
For giving me the
There is
opportunity.
a last question, I guess. Is there an expanding universe theory that considers a 4D Mobius strip fabric?
Oh, beyond my pay grade. Can't even think about that one. I gotta go find a cool YouTube video explaining that.
No problem. You've done great. Thank you.
Thank you.
What I would like
Wonderful.
to do now, unless somebody else has comments right now, I'll move to the questions unless somebody here has comments. All right. I am going to give the answers to the questions that I asked at the very beginning. And our winner will be J Manifold for the first question, M30. It's a globular cluster and Capricornus, magnitude 6.9. It will rise in the east just as dawn starts to break. So catching that before daylight is the challenge object in the Messier Marathon. Cassini, it is Cassini A that is the large crater that sits a little off center in the crater of Cassini. And Dusty Haskins has answered that question. The last big bird question to me here is, it is the aftermath of supernova 1987A, and that irregular blob in the center might be heated from an enshrouded neutron star. The bright ring surrounding it consists of material that a star released 20,000 years earlier. The supernova's shock wave is lighting the ring. I think that's amazing. I saw that and that just amazed me. The correct answer was given by Liam Plybon. So thank you all for answering that. I would like to let you know, thank you for attending, but our next Astronomical League live event will be on March 12th at 7 p.m. and Dr. Barbara Harris will be our speaker at that time.
All right.
Yeah, so we hope to see you then, and I will quit sharing my screen there.
I don't think you were sharing your screen.
There we go. Thank you, Scott. And if there's, what did I miss?
You weren't sharing your
You weren't
screen.
sharing your screen.
Oh, that wasn't very good, was it? Somebody next
I
time.
thought it was just like seeing something invisible or something.
No, do you want me to run through those again? Or are we good?
I think
Somebody
we're
next
good.
time
I think
tell
we're good.
me.
I will. There
know,
was
people.
one other comment here from Claude Plymate, who a professional astronomer that's worked at Kitt Peak and also at the Big Bear Solar Observatory, and he says, "Excellent talk, thorough and very clearly presented." So
Thank you.
it's a big compliment. So, yeah.
Thank you. Does anybody else have any comments here before we wrap up?
They're saying awesome. Thank you so much, Terry. You know.
Oh, thank you, Scott. Thank you for doing this. Thanks everybody for attending. Rachel, fantastic job. Thank you so much. Don, very much appreciate your talk too. And everybody else here on the league. Really appreciate you being here, and all of our visitors that are also sitting here listening. So thank you all very much. Please catch up with us on March 12th with Dr. Barbara Harris. Thank you very much, and we'll see you next time.
Okay.
Thank you.
Take care.
Bye.